Hello, everybody. How's it going? So I have prepared for you guys kind of a correct Wikipedia rabbit hole, if you will, in some kind of sequential order of theoretical or mathematical physics. So if you essentially what I mean is if you were to just go on the correct rabbit hole, you would kind of follow the trajectory of this video and learn about these things like I guess as we go or something. But so I'm going to be doing this without any equations, without any sense of mathematics, but I will be mentioning the mathematics as used. Um, so that's kind of the idea. I'm just going to be talking the slop on my monitor. I'm going to be sharing like the knowledge that I have about physics and reasoning through this kind of thing that I have prepared. But yeah, so we're going to start here with the principle of least action, which the subject of mechanics is concerned with primarily particles and trajectories, and you know, uh, basically single particles or rigid bodies in three-dimensional space, with these deterministic type of trajectories that obey the principle of least action. Now, what this is probably the most important thing to understand is because this is going to appear across every kind of instantiation of physics as we keep going on to quantum, etc. And what's important about this principle of least action, or what's important to understand, is that it is kind of a function, or it is a minimization of a functional, and it's the foundation of uh, variational calculus. Okay, or it's what the invention of variational calculus um, was all about. It was actually historically trying to solve um, this particular problem. That if I had like to draw some kind of curve, where if I rolled a ball down this particular slope, what is the parameterization of the curve, or how do I parameterize the curve in such a way that um, this ball gets there in the least amount of time? And so that's really what this was. This is what the kind of problems that mechanics is all about. It's about systems. So the deeper physical principles come from the homogeneity of time and space and the isotropy of space, which basically means if I were to do a laboratory experiment, I don't know, in Japan versus a laboratory experiment in North Carolina. Um, Basically those, and if I were to do them the exact same way, and even maybe at different times, they should fundamentally give me the same results, assuming that space itself is homogeneous. And then the isotropy of space says that if I were to have a lab in space, in the vacuum of space, and orient it in different ways, it doesn't matter the orientation of physics, or the orientation of the experiment, it should still give us the same result. And we kind of observe this in space as well. So these two notions lead to the idea of let me change my, I like this better. These two notions lead to the idea of conservation of energy, momentum, and angular momentum directly. So conservation laws directly come from these particular principles. And now, what the principle of least action is going to do is it's going to give you the systems, or the systems of differential equations that you then would convert to integrals of motion to solve for various systems. Among those systems that you should study are the Kepler's problem for inverse square law fields and the conic section orbits. So just like, here's the Earth, right? And then here's the sun. And the Earth goes around the sun maybe elliptically, or maybe like circularly, or maybe like hyperbolically, or parabolically. Okay, something like that. And this comes directly from Abel's integrals of motion. Okay, so now the disintegration of particles, elastic collisions. This would be like scattering types of phenomena. Um, Particles that, well, scattering is kind of the opposite of collisions, but you have, again, they are fundamentally, the equations that we have fundamentally work because of the conservation of energy, momentum, and angular momentum that we originally had. Okay. Now let's move on. We're going to replace particles with fields now. So particles themselves are kind of replaced with continuous, or in other words, classical fields. And this absolute variable of time is going to be abandoned for basically four-dimensional. For the fields themselves are going to be in four-dimensional pseudo-Euclidean continuum. Now, what's important to note about about continuous fields and the notion of space-time is that we'll begin with the idea of covariance, or the principle of covariance, and four tensors that transform under Lorentz invariance. And of course, the principle of least action extends from just over particles and from time over doing variations over four-dimensional volumes. Okay. Now, so that's what's important. And then, of course, they have to, with the idea of Lorentz transformations and gauge invariance, the four tensors, or the electromagnetic four potential, allows us to create this field, electromagnetic field tensor, that encodes both the electric and magnetic fields. And so then from there, you can talk about propagation of light, geometrical optics, fields of moving charges and retarded potentials and Liner-Witcher potentials, and also radiation of electromagnetic waves, Poynting vectors, dipole radiation, all of these things. So all of that comes from the formulation of what is a field, essentially answering the question of what a field is. So going from particles to fields plus relativity. And then finally, we end with the idea of, in curvilinear coordinates, and the notion of covariant differentiation, gravity gets reduced from just being some kind of force to just being the curvature of this space-time metric, where we get rid of the notion of Minkowski space-time, but we're working within a space-time that has a metric that's not engineerable, but that depends, that encodes the geometry of space-time, such that the parallel transport gives us holonomy for gravitation and all of these things. So the gravitational field equations come from Einstein-Hilbert actions, and physical laws are entirely dictated by the symmetries and geometric properties of the space-time continuum. All right. And then, of course, it's important to realize then that some of these field equations, then some popular solutions of the field equations govern all of relativistic cosmology by just taking the isotropy and homogeneity of space, again, very seriously. By taking this conservation laws very seriously, you get the finite time universe. And so that's where we get the 13.4 billion years, or 13 point something billion years, age of the universe, by also examining the cosmological redshift and gravitational collapse. And singularities are also interesting gravitational phenomena. Okay. So next, moving on from fields and we had mechanics, fields, particles. Now, particles themselves. Basically, we're going to break the classical determinism of the particles. And how to think about this is we're going to replace. We're going to think about things in terms of things called wave functions in quantum mechanics, and Hilbert spaces, operators, and Feynman diagrams are basically the thing that we're going to cover here from quantum electrodynamics and just quantum mechanics as a type of mathematical theory, and then going into how relativity tends to get manifested in the quantum mechanical domain. So we'll first start with trajectories in phase space are abandoned. So, by the way, phase space just happens to be a different formulation of the integrals of motion for various systems. It turns out that there's something called Lagrangian and Hamiltonian mechanics. There are two different formulations. The phase space is very emphasized in Hamiltonian mechanics, okay, which basically just says if you have some momentum and some position, you would describe some trajectory in phase space that would describe some movement of a particle or some trajectory of a particle parameterized. Okay, so anyways, and I just deleted a little bit of that cue. Oop. Okay. So yeah, phase space is important, but the definite trajectories are abandoned. So it's more fundamental to think of them as operators, or to think about operators acting upon quantum states. So the uncertainty principle is just the resolution of the position momentum in phase space, given that there's a cap on uncertainty. And the complex wave function in Hilbert space is going to be governed by superposition, and determinism is going to be replaced with probability amplitudes. Now, what's important to note is that physical observables themselves basically, the energy, momentum, angular momentum, these three physical observables, they're no longer scalar values, but they become these kinds of like algebraic objects that are non-commutative, or that are compatible with the non-commutative geometry that kind of emerges from quantum mechanics for operators and Hilbert spaces, etc. And so you have these in physical states. It's basically a triple, right? So you have these Hermitian matrices and differential operators that start replacing the concept of physical observables, and the outcomes of measurements are restricted to the spectra of the operators themselves. Okay? And so this is a lot more algebraic rather than straightforward of a description of some continuous field or some singular particle. Okay? And it's just also a lot more realistic to describing why light gives us different colors, and why we have things like black body radiation, or why molecules and the hydrogen atom, it allows us to solve the hydrogen atom as well and explain such things. Group theory and representations of continuous and discrete symmetry groups are core part of quantum mechanics. This is this should be emphasized. And we apply these math tools to classify molecular vibrations, electronic spins, and Pauli matrices and spinners. The theory of electronic spin is governed by Pauli matrices and spinners, and Clifford algebras, and projective geometry. The principle of indistinguishability, it just basically tells us that the behavior of particles, how they are chosen to be enumerated with wave functions, they must be either symmetric or anti-symmetric, and I can't spell. Bose-Einstein and Fermi-Dirac statistics both kind of emerge from the fact that you need, in order to have to have a vector space, basically, for the anti-symmetric or symmetric parts, for them to satisfy vector space, it's only possible to have bosons and fermions, which then leads us to quantum electrodynamics. But also the Pauli exclusion principle, which states that two particles cannot occupy the same state unless they have different spins. It just depends on for fermions specifically. and then also the exchange interaction as a concept as well should be is really well motivated after kind of going through all of these things. Okay, and then quantum electrodynamics, you'll have the Dirac equation for fermions. I didn't mention it, but the Klein-Gordon equation for um, uh, yeah, I think bosons. I'm sorry, for spin. Okay, for spin zero. Um, uh, yeah, for spin zero systems, they would be described by the Klein-Gordon equation, and then for relativistic wave equations, you get the Dirac equation. The Klein-Gordon equation has a couple of problems. I can't remember. It has something to do with like a singularity or something that needs to get integrated out. Um, but that gets handled. It's still a relativistic wave equation. The Dirac equation just kind of like factorizes, or like it's like the square root of the Klein-Gordon equation, which makes sense. Now the quantization of the electromagnetic field, that's what it is. The quantization of the electromagnetic field is what the Klein-Gordon equation is all about. You have to quantize it. That's right. And then the treatment of the scattering matrix, so just kind of some from initial state to some final state, assuming some really basic things like unitarity, etc. And then the perturbative kind of diagrammatic techniques called Feynman diagrams to treat the S matrix with. There's also quantum phenomena that are dependent on the finite velocity of light. So just the fact that the velocity speed of the propagation speed of light in a vacuum is finite, we have to reconcile quantum mechanics in this way. So that's kind of what you would want to investigate with quantum electrodynamics. Ultra relativistic scattering, radiative corrections, and then justifications of renormalization and effective physics. All of that kind of wraps up quantum and quantum electrodynamics. Okay, this would be just more kind of under the realm of quantum theory. Quantum theory is also very mathematical, if you can tell. Yeah, and quantum theory also kind of usually introduces a bit of statistical mechanics as well, but not yet. So that's kind of the prelude to the statistical physics. So with statistical physics, we're trying to, the core objects here that we'll be playing around with are like ensembles and distributions, hence statistical physics, right? You want to think about statistical physics, especially this segment, as equilibrium statistical physics. So we want to explain how the macroscopic kind of thermodynamic quantities and phase transitions of materials, like ice to water, or I guess ice is water, but ice to liquid to gas to vapor. All of these things emerge from these microscopic and reversible microscopic laws. So we want to avoid something called the ergodic process, and this or the ergodic hypothesis. So this was pioneered by Boltzmann and Maxwell, and it basically said that for an infinite period of time, a closed dynamical system will visit every accessible microstate in phase space. That's what the ergodic hypothesis is. And so the long-term average of some physical quantity would equal its statistical ensemble average. Now, this is a problem because obviously laboratory experiments of physical systems are done in finite time, right? So there's another thing we can talk about is quasi-closed subsystems. And this kind of allows us to get, for statistical physics, and this is usually how it's taught now. We don't really talk much about the ergodic hypothesis anymore, for physicists at least. There's still the mathematicians still like are interested in, infinite time periods for systems, for closed dynamical systems. But for the sake of understanding physics, it suffices to work with closed subsystems, which is like a macroscopic body is going to be a collection of smaller but still macroscopic subsystems. And the continuous interactions with the remainder of the total closed body acts like a thermal bath acting on the system. And so when we do this, what's important to note is that this allows us to construct these objects like partition functions, and just basically go from micro to the macro equilibrium. And these microscopic types of laws are going to depend on a very large number of degrees of freedom. So that's kind of what's replacing the statistical, or subsystems are said to be statistically independent from each other to then derive these canonical distributions, microcanonical or grand canonical distributions. And so you have entropy, temperature, pressure as these thermodynamic quantities that come directly from these particular distributions. And the Boltzmann distribution for ideal gases, the law of equipartitions, which basically gives us that kinetic energy is quadratic, and then it's equipartitionable because they're independent. And then molecular collisions, quantum Fermi-Bose distributions. All of these things are going to lead to this development of this kind of more quantum statistics, leads to the development of blackbody radiation and degenerate electron gases. And then also the order parameter theory, phase transitions, conditions for the Clapeyron-Clausius formula, critical point, symmetry breaking, order parameters. All of these things kind of get covered in the realm of statistical physics. Okay. Now moving on to this one, which is continuum mechanics. As you can see, it's kind of a massive field. Okay. But basically, we're going to apply statistical. We're basically applying statistical averaging to the idea of bulk matter. All right. So bulk matter themselves. This is where all of your very nonlinear partial differential equations comes from. The Navier-Stokes equations, elasticity, invoking the continuum hypothesis to solid deformable matter. All of these things are going to depend on how we choose to think about changing our conceptualization of discrete atomic matter to smooth over, and they're going to become continuous density, velocity, stress, and strain fields themselves. And one would probably want to look at the fundamental equations of fluid dynamics for Euler's and Bernoulli's equations for ideal fluids for mass, momentum, and energy conservation. Again, this always comes back. Except this is mass conservation. So this is because we're going to be working with velocity fields instead for describing more of the fluids. Dissipative forces, Navier-Stokes equation for viscous fluids, and energy dissipation for thermal conduction. There are complex phenomena like laminar boundary layers. You probably should also, if you've ever seen laminar flow, if you've never seen laminar flow before, you should quit the video, go look it up. It's pretty interesting, and go on that tangent hole, go on that rabbit hole. It's a pretty interesting phenomena. Turbulence itself is a successive infinite excitation of degrees of freedom for increasing Reynolds number. So that's kind of how that's the formulation of turbulence that would be more in alignment with theoretical physics. Less mathematical, but more theoretical physics. The gas dynamics, combustion, relative fluid dynamics, and macroscopic hydrodynamics equations governing superfluids. Okay, and so these types of basically we're going from the discrete, basically from discrete itself, atomic matter, and statistical phenomena to these smoothing over um, uh, to continuous media itself. And then as we invoke the continuum hypothesis, which is a mathematical hypothesis actually, that plays a very important role in physics, we have that we will get waves in these particular types of continuous media that we need to explain when you detail away, or when all of the atomic coarse-grained types of details are smoothed away. And that's going to introduce dissipation and nonlinearity. So we'll get phenomena like turbulence, shock. So yeah, I mean, the physical state of a deformed body, of a solid deformed body, is mathematically captured by the displacement vector and symmetric strain tensor. Internal restoring forces arise from deformation described by the stress tensor, and free energy becomes a function of the strain tensor. And by the way, free energy comes from the generating from the partition function in statistical mechanics to then describe order parameters, or basically describe like all of the thermodynamic quantities and stuff. Hooke's law defines the modulus of compression rigidity, Young's modulus and Poisson's ratio. All of these become very important in elastics and even engineering. A lot of engineers use these results, or not results, but these disciplines in theoretical physics. Really, continuum mechanics is the realm of a lot of engineering, and but it is completely a field of theoretical physics that's worth going into. The rigorous equations for equilibrium, bending of plates, so like flexural rigidity, torsional rigidity of rods and curved shells, the propagation of elastic waves in isotropic media, so if we separate longitudinal compression into waves and transverse shear waves, anisotropic crystals, and exponentially damped Rayleigh surface waves. These are all kind of observable everyday type of phenomena that basically you could even play around with some solids, or if you have like any of those like stress balls or whatever, and like want to play around with compression and the waves and shock waves and dampening of elastic materials. This is like very much the type of theoretical things that you'd want to emphasize in your Wikipedia rabbit hole search. But there's also the mathematical descriptions of defects in the continuum, stress fields created by linear dislocations, characterized by Berger's vector and the equilibrium of cracks, and the mechanics of fluids, crystals, and continuous symmetries are broken in soft matter to create orientational order in pneumatics, spiral structures, and cholesterics, and one-dimensional periodicity symmetrics. That's the way to say that. But yeah, all of this is continuum mechanics. It is a very, as you can tell, I talked a little bit less because I'm less familiar with this field, but it's very interesting, and I look forward to reading more up on continuum mechanics. Next, the electrodynamics of matter, as well as it kind of goes into condensed matter physics as well. But basically, it's just combining electromagnetic fields and with continuous matter itself. And you'll get these the core objects here that you would want to think about is polarization and magnetization. So electrostatics are in conductors and dielectrics. You'll have these thermodynamic regulations and electrostriction and piezoelectricity. These are physical things that are the subject of a lot of theoretical physics, and among these particular things are the Hall effect, magnetic symmetry in crystals, properties of ferromagnetics near the Curie point, including magnetic anisotropy, domain structure. Also, magnetohydrodynamics, the electrodynamics of conducting fluids, propagation, dispersion, and scattering of electromagnetic waves in isotropic and anisotropic media. These things are all pretty much very much important for the development of modern technology and how our phones and computers and laptops and everything works. So it's important to pay a lot of attention to these things. And then the more interesting stuff is the Ginzburg-Landau theory of superconductivity. Now, the Ginzburg-Landau functional basically is one of the culminations of the electric field and matter, as in kind of engineering science, because it's phenomenological, but it's a very powerful application of the ideas in quantum electrodynamics to superconductivity for the order parameter types of, or sorry, from not quantum electrodynamics, but it's a application of statistical mechanics to the electronic response of. I mean, we're basically working with continuous media that display statistical, that are basically smoothed over statistical properties of atoms, that have some special. A lot of the physics is really unknown because it just gets really complicated. But what's important to note is that this is a phenomenological model, but it's a free energy functionals that are constructed to describe. Free energy functionals are always constructed to describe polarization, magnetization, and superconductivity. And so that's why I kind of have them in this intersection here before we get to condensed matter. So that's just my opinion. Maybe I kind of butchered that, but that's what I can do so far. But yeah, so this complex scalar field and pseudo wave function, or the order parameter, are constructed, and it's basically the squared magnitude of this function is that the local density of superconducting electrons. And if you take something called the ratio of penetration depth versus the ratio of coherence length, it allows you to classify superconductors by type 1 superconductivity and type 2 superconductivity, where you have like these formed triangular lattices of quantized flux tubes or magnetic flux with vortices that are kind of going through the material that allow it to kind of float in midair basically, and do all kinds of stuff with enabling us to not have any resistance or electrical resistance that causes any particular heat or whatever. Basically, it formulates these ideas of like super currents and all of these things. So it's very cool. Now we'll go on to condensed matter. Basically, with condensed matter, you are going beyond the idea of ideal gases to studying heavily interacting systems using these Matsuraba techniques or diagrammatic techniques. So it's just basically Feynman diagrams applied to finite temperature condensed matter. And so that's kind of the theory that you would want to look at. The macroscopic theory of quantum liquids, Fermi liquids, helium-3 or electrons and metals, and Bose liquids, building upon the quantum field theory kind of aspect as well for superfluid helium-4. And the microscopic or macroscopic properties of the liquid behavior of these excitations of elementary particles to create these quasi-particles, elementary excitations in continuous media to create these quasi-particles that it looks like weakly interacting particle behavior and more exotic types of topological quantum fields moving in a background mean field. So because they have a background type of field, we get different kinds of weird phenomena like skimerions or skymerions and anions and all of these and even graviton type spin 2 fields as well can be found in condensed matter systems. And if you don't believe me, just look up a Nature publication. It's like one Google away. Okay, so yeah, gravitons are technically or spin 2 fields are effectively in quasi-particles are there. And so dispersion relations for these excitations like phonons and rotons, the existence of multiple wave propagation modes, superfluids, including second, third, fourth, and fifth sound. That's pretty much the background or the foundation for condensed matter. And now lastly, we will work through non-equilibrium physics and kinetic theory. The main idea is that we're going to go from equilibrium to non-equilibrium and define transport equations and Green's functions and distributions themselves. So generalized distributions. So the microscopic theory of processes and systems that are not in statistical equilibrium essentially is what we're working through. And the evolution of these systems are governed by the Boltzmann transport equation. Basically, you need a description of how the distribution function evolves over time and relaxes to thermodynamic equilibrium through particle collisions. And the formal proof of the H theorem, or the proof of the law of entropy increase, is also something you would want to look through as well. The principle of detailed balancing, methods for calculating kinetic transport coefficients such as thermal conductivity, viscosity, and diffusion across various media. The dynamics of collisionless particles, where the charged particles interact primarily through these long-range, self-consistent electromagnetic fields rather than binary collisions. So, again, this goes back to classical fields, where particles themselves their fields interact. Their continuous fields interact, not just the particles themselves, but the particles can then transmit. Basically, the whole idea is the plasmas are never actually colliding with each other, but because they're charged particles that are moving around in this soup, their fields are affecting each other, and so that's kind of what you would want to think about. Landau damping. So even in strictly collisionless plasma, the Boltzmann equation set to zero. The collision integral. Longitudinal electron plasma waves, called Langmuir waves, experience exponential damping over time, and this dampening is caused by wave-particle resonance. And so this is a phenomenon that if you have electrons moving slightly slower than the phase velocity of the wave, they can surf on the wave's electric field and are accelerated, absorbing the energy from the wave. But electrons moving slightly faster than the wave are decelerated. All right, that's not really a word, but they're it just makes sense. They're decelerated. It's a directional acceleration. They are slowed down. Okay, imparting energy to the wave. So in plasma in thermal equilibrium obeys Maxwellian velocity distribution, and there are more cold particles moving slower than the wave than hot particles moving faster than the wave. And that's just kind of the new idea of equilibrium, right? Even though it's in a non-equilibrium, it's kind of an effective equilibrium that emerges out phenomenologically. Okay. The net transfer of energy from the collective wave mode to the kinetic energy of the individual particles causes macroscopic waves to damp out without any irreversible thermodynamic collisions. And then you have contour integration in the complex plane. This is a nice mathematical technique to resolve particle resonance singularities, and it's called Landau's rule. Okay, and basically just leaves kind of an imaginary part that from the residue um, as you integrate or as you resolve the resonance around the singularity. And this goes also back to the S matrix back in QFT, or sorry, not in QFT, in quantum electrodynamics. Notice I didn't mention QFT. Quantum field theory is kind of it's a field that applies pretty much in flavors everywhere, if that makes sense. Everywhere past quantum electrodynamics, QFT kind of applies in statistical, quantum continuum, electrodynamics of matter, but yeah, Feynman diagrams, perturbative quantum field theory, non-perturbative quantum field theory, string theory, all of these things kind of are not exactly theoretical physics. These are more mathematical physics types of endeavors. I know I might get some hate for that, but that's kind of the truth. We're focusing specifically on theoretical physics here. Okay. But yeah, finally, the last thing we're going to end on is quantum kinetics. So just the transport equations for quasi-particles and Fermi Bose liquids, electron-phonon interaction, metals. All of these things kind of get covered with quantum kinetics. So yeah, that's pretty much what we have here. And of course, there might be some diagrammatics as well for the some, I guess, field theory diagrammatics for kinetic theory as well. But yeah, so I mean, the grand arc is this. You start off with these point particles that then become fields, and then, you know, in quantum mechanics we start dealing with wave functions and probabilities. Statistical physics, we construct ensembles and distributions of quantities, and then we talk about continuous media, and then finally just interacting quantum systems. Okay, so the mathematical sophistication, understanding that the mathematical sophistication from here, like in ordinary differential equations that pop out of the principle of least action, it gets really it exponentiates over to partial differential equations and functional integrals, diagrams, all of these things. So hopefully I achieved some kind of internal consistency and some unity of theoretical physics, and basically just thinking about the physical intuition and just pure physical intuition from this video. Okay, so thank you guys very much for watching, and I'll see you guys next time.